Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to look at section 4.4, where we're going to look at the concept of basis and coordinates. So what is a basis? So basis for a vector space is nothing but a collection of vectors that do two different things, okay? One, they have to span the space, and then the second conditions is that they have to be linearly independent, okay? So we have, say, for example, in R2, we know that our typical vectors I and j, they span the entire vector space R2, and you can verify them very easily that they are also linearly independent, so they form a basis. So basis is optimum sets of vectors that can reach every vector in that space, and they are no redundancy, okay? So in R3, we know that our standard ijk vectors, okay, is a standard basis. Obviously, they span the entire space, and they are also no redundancy. So they are all linearly independent, okay? So for each basis, we can associate a concept what they call coordinates. So the coordinates will be related to a basis. So once we have a basis determined, we have a basis set, then we will be able to talk about the concept of coordinates. We'll look at it in detail in this video. Another thing you have to know is that basis does not have to be unique. For a particular vector space, you can have many different bases. So for example, in R2, this is our standard I and j vectors, but if you have another vectors that looks like this, it will again also form a basis in R2. We can show that pretty easily. If you have another vectors that is like this, these two vectors, they are not the ij vectors, but they can also form a basis in R2. So basis for a particular vector space does not have to be unique. In fact, we have many different bases, okay? So same thing, let's say in R3, this is our standard basis, but you can see they are orthogonal, which means they are 90 degrees to each other, but they don't have to. If I move the angle like this is again going to form a basis that is in R3. So as long as they span the space and they are linearly independent, they will be a basis. So basis need not be unique. So for different bases, you will have a different coordinate system, okay? So we'll talk about that. But remember, bases need not be unique, okay? So we'll talk about all that right now. Let's get right to it. All right, and let's begin by looking at the objective for this video. So at the end of this video, you should know what does it mean for a set of vectors to form a basis for a vector space. And given a set of vectors from a vector space V, you know how to determine whether that set actually form a basis for that vector space or not. And given a basis for a particular vector space, this is a basis. And also you're given vectors that is in that vector space, you should know how to write down the coordinates of these vectors relative to this basis. Okay, so let's look at a very simple example. So we are in R2 and we have a set consists of these two vectors. And I hope you can see that this set spans R2. This is very obvious and they are linearly independent, okay? Why is it obvious? Because if you give me any vectors that is in R2, I know exactly how to reach them. The reachability criteria is very straightforward. You know that I need A of these vectors and B of these vectors in order to get these vectors. So AB is reachable by these two vectors in a very obvious manner. Like this is super trivial. You can see that. And also in terms of linearly independence, you can see if you want to reach these vectors, these zero vectors, there is only one way you can do that, which is this. So by the definitions of linear independence, you know that this collection of vectors, these vectors here and here, these two are linearly independent and they span the space. So in R2, this is the optimal collection of vectors that can reach every elements that is in R2, and there's no redundancy, okay? So no redundancy, and also a collection of vectors that has no redundancy and also can reach every vectors in that vector space is very special. They are known as a basis for that vector space. So this is a proper definition for the basis. So if you have a collection of vectors that can do two different things, okay? Number one, they span the entire vector space V. That means that every vectors in the vector space V can be reached by doing can be written as a linear combinations of all these vectors. That's a proper terminology. And there are no redundancy. That means that they are all linearly independent. If you can find a collection of vectors for a vector space V that can do these two different things, that have these two property, then we will say that that collections of vectors is a basis. It's a basis for that vector space. So we have seen that in R2, this is actually a basis for vector space R2, and these are known as the standard basis because it's very easy to see why they are basis. And for people who are studying physics and all that, you should know this is actually your vector I, and this is your vector J actually, right? So these are the standard basis. And obviously you can extend this very easily to the vector space Rn. So this is the standard basis for the vector space Rn, and you can kind of see why the span, okay, it works, right? Because every vectors in Rn can be written as a linear combination of these vectors in a very easy manner. You can kind of see how to do that. And they are also very obviously linearly independent. So they form a basis for Rn, okay? So these are also known as the standard basis for Rn. Okay, so let's look at another example, okay? So right now, we are still in R2. We don't want to get too ambitious yet, so we are still looking at some of the vector space that we are very familiar with. And you are given a collection of vectors. So you have a set which has these two vectors, okay? You have these two vectors. And the question is that whether or not this set is actually a basis also for R2. Is it a basis for R2? Every time when you have this question, is the collection of vectors, this collection of vectors form a basis for R2? You just have to do two different things. You check the two property, okay? So number one, you have to check that whether they span R2, that usually that's the hardest things to do, and then you check whether they are linearly independent. So if you have the answer for the span, you usually have the answers for linear independence pretty easy, okay? Let me show you how, okay? So just like what we have learned from before, in order to show that these two vectors span R2, you have to select an arbitrary vectors that is in R2 and see whether we can find, okay, we can find scalar k1 of 1, -1 and scalar k2 of 1, 2 in order to get to that AB. And we have seen from before that the answer is yes, and we actually know exactly how the K1 and K2 should be selected in order to reach AB. And so this is how you should select them in order to reach AB, okay? So this is not so obvious. You actually have to do some computations, and the way to do the computations is just to solve the system of linear equation. We have seen that before, and this is not like the standard basis where these coefficients can be easily determined. This one you actually have to do some kind of computations. So the span part works pretty well, and as I said, if you have the answer for the span, you will have the answer for linear independence pretty easily because this is for all AB. So in particular, if you select this to be 0 and 0, so you will see that the coefficient here has to be 0, the coefficient here has to be 0. So you will see that in order to reach the vector 0, the 0 vectors, there's only one way to do it. That is, this has to be 0 and this has to be 0. That's what I'm saying here. So because of that, you can also see that these two vectors, they are not only span the entire R2, but they are also linearly independent. Therefore, by the definition right here, they are considered as a basis. They are considered as a basis. So this is also a basis for R2. All right. So what we have seen, what we have just shown is that basis doesn't have to be unique. Okay. So you can actually have a vector space that have many different bases. So in R2, we have seen that this is the standard basis. This is the collection of vectors that has these two properties. And we also just show you that in R2, this collection of vectors also have that two property. So this is two different bases for R2. So R2, okay, has many different bases. So the basis for a vector space, they need not be unique, okay? All right, so now let's extend this concept of basis to other vector space. So we are sick and tired of R2 and Rn. So now let's change it to another type of vector space. Let's say we are looking at polynomial of degree at most 2. Now, I claim that this is a standard basis for this vector space, okay? So why is it a standard basis? It's pretty easy to see that they span the space. It's very easy to see a span the space. And it's also very easy to see that they are linearly independent, okay? So let me show you why I say that you can easily see that this collection of vectors, so these vectors, there are three vectors here, okay? So this collection of vectors spans the entire P2. So take an arbitrary element. The techniques is the same. So in R2, you take an arbitrary element like this, as in R2. It is fixed, but it is arbitrary. And so here in P2, we are going to take an arbitrary element that is in that set. So we'll take a polynomial, okay, the arbitrary polynomial that is in P2. So this, as you can see, in order to get to this polynomial, I need one of these vectors. I need A of these vectors, okay? And then this is the vectors right here, okay? And then I need B of these vectors, okay? That's the vectors right here. And I need C of these vectors, right? So any A, BX plus CX squared, you can reach them by taking A, right? This is a scalar, right? Taking A of these vectors, B of this vector, and C of these vectors. So in terms of span, there's no problem whatsoever. So this collection of vectors actually span P2, okay? All right, and it's in terms of reachability, in terms of linear combinations, it is very easy to see what should all these coefficients are, okay, in order to get to that vectors. Now, obviously, if you want to look at a zero vectors here, so the zero vectors here in our case is a zero polynomial, and you can also see that it's only one way to do it. In order to get to that zero polynomial, using these three vectors, the coefficient here really has to be zero, okay, and has to be zero. You have no other choice but to have all this zero. So they are linearly independent. These three vectors here are linearly independent, okay? So you have a collection of vectors. They are spanning, the span is the entire P2, and they are linearly independent. So by definitions, this collections of vectors, this sets S, form a basis for P2, and these are known as a standard basis for P2, okay? So again, we are in the vector space P2. So now I'm asking you to show that this is also a basis for P2. So we have a collection of three vectors. We have 1 plus x, we have one vectors here, we have x plus x squared, and we have 1 plus x squared. And your job is to show that this particular collection of vectors also form a basis for P2. So we are not doing anything new here. In fact, we are just putting together the stuff that we know from the previous sections. That is, you have to verify that they span the entire P2, and you have to verify that they're linearly independent. So we know how to do that already. So I want you to practice on it, and I will see you in a little bit. All right, I will give you a moment to think about these problems, and you should pause the video. And when you think you have the solutions, you can restart the video and we will compare our solutions together, okay? All right, welcome back. So how do you show that this is also a basis for P2? Well, follow the definitions. 70% of the time in this course, when you have to solve for problems, you just follow the definitions. So there are two things that we need to show. We need to show that these three vectors here span P2, okay? And then we want to show that these three vectors here they are also linearly independent. So let's set up this equation for span. Take an arbitrary element that is in P2. So let's call them the polynomial, the arbitrary polynomial A plus BX plus CX squared. So let's see whether or not we can write this as a linear combination of that three vectors. That means that we have to identify the K1, K2, and K3. So, okay, let's look at this system here, and let's try to solve for K1, K2, and K3. So if you compare the constant terms, you will get this. If you compare the coefficient for x, you will get this. If you compare the coefficient for x squared, you will get this. So even though this system here, this is equations involving polynomial, but this system right here has nothing to do with polynomial. We have three equations involving numbers, K1, K2, and K3, and also numbers A, B, and C. So again, A, B, and C are fixed. These are not variable. A, B, and C are not variable. The variables that you have is K1, K2, and K3. So K1, K2, and K3 is unknown. Now, you can actually put this into a matrix system. You can also put it into an augmented matrix and started to row reduce to identify what the K1, K2, and K3. That is one way to do it. It's harder to do it that way because you have A, B, and C. So you can't really use a calculator. Your calculator can deal with A, B, and C, so you have to reduce it by hand. So if you do it that way, you can actually get something that kind of looks like this, where you can I clearly identify what should be your scalar, right? You clearly identify how is your scalar related to this vector AB. So if you have vectors AB, you will have this and this. If you have vectors CD, you will have this things that here have to change to CD and so on. So, but you know exactly how they are related. And when I say exactly how, I really mean exactly how they are related. That's one way you can do. You can solve it by really finding out what is the K1, K2, and K3, and obviously this K1, K2, and K3 will involve this variable A, B, and C. You can do that. Alternative, there's another alternative. The alternative is that I don't have to do all that computations. In fact, in order to show that these three vectors here span P2, I just need to show that this equation has solutions. I just need to show that there exists this scalar, there exists this scalar K1, K2, and K3 such that this equation is true. All right, so I just need to prove existence. That's one way to do it. Okay, so if you are busy and you don't have time, you'll be like, I'm not going to tell you exactly what are the K1, K2, and K3, but I'm going to tell you those numbers exist. So if you think of it that way, this is easier to do because you look at this system. Let me write this system as this. Okay, how do you know that this system has a solution? Well, you look at this matrix here. Okay, you can show that this matrix is invertible, because if this matrix is invertible, the answer is this. We know that if you have a linear system like that, and the matrix here, if it is square matrix, only when it is square matrix, okay, because non-square matrix, you can talk about invertibility. So if you have a square matrix here, and if your square matrix here is invertible, we know that we have a unique solutions, okay? What are the solutions? Well, do this computation and you figure it out. But we have unique solution. We know that we have a unique solutions. So how do you know that this matrix is invertible? Well, you can compute the determinant. If you compute a determinant and show that the determinant is not equal to 0, then you can claim that the system has a solutions, therefore it spans. Right? So how does it span? Well, compute this if you want to, but if you are in a rush, that is actually a way to deal with it. We will be like, I'm not telling you how is your K1, K2, and K3 related to the A, B, and C, but this equation here surely have a solution. Okay, the reason why we are dealing with the coefficient matrix only is because your coefficient matrix are all numbers. You don't have to deal with A, B, and C. Right? So this simplify our computations. So you can do that. And once you have span, linear independence follow pretty easily, because for linear independence, so this is our zero polynomial, which means that you are basically solving the same system, but now this is 0. So again, if your matrix is invertible, your solutions is actually A inverse multiply 0, 0, 0, and you don't have any other choice. Your K1, K2, and K3 has to be all 0. So this is what is said here. So the span part, this is an alternative method to show that the three vectors spans P2, and therefore you can also see that independence follow pretty easily. So now we have another vectors, collection of vectors that form a basis for P2. So P2 have this as a basis. P2 can also have this as a basis. So again, we have seen that basis need not be unique. Okay, we don't have to be, in fact, we have infinitely many different bases for a vector space. So basis need not be unique. So this is one thing you should always remember. Now, I just want to give you a quick example on another vector space. So this is a vector space consists of all the 2x2 matrices. And it's very, very easy to see that this is a standard basis for this vector space. Standard basis because you can see how it spans the space, and you can also see how they are independent. You don't even have to do any computation. You can just see it. So these are the standard bases for the spaces consist of matrices. Okay, and again, you can find in your homework. You can also find another basis for this vector space. So again, for every vector space, you can always find more than one basis. Okay. All right, so now we want to switch topics and talk about another concept. That concept is coordinates, okay? So let me give you this theorem first, okay? And I state and prove this theorem, and we'll say more about what is a coordinate, okay? So now this theorem says that, okay, for a vector space V, choose a basis, okay, and then don't change it, okay? Choose the basis, all right? Okay, so this is a fixed basis, don't change it, okay? So this basis here has this vectors, V1, V2, okay, all the ways to Vn. So you have a basis that has all these vectors. So if you take an element that's from this vector space, obviously this vector can be expressed as a linear combination of v1, v2, all the way to vn, because bases, one of the property for bases is they span the space, right? So every vector is reachable by this v1, v2, all the way to vn. So if you have a vector v, we can write it like this. And this theorem says that there's only one way to write it, okay? So there's only one way to write it, because if you try to write it differently for the same vector v, let's say you write as d1 v1 plus d2 v2, all right, plus dot 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 plus dn vn, all right, then this d1 here must be the same as c1, this d2 here must be the same as c2, this dn here must be the same as cn. That's what the theorem said. You can only write this particular expression here in one and only one way. Another way of you writing it is, turns out, will be the same as this one, okay? There's only one way to write that. That's a uniqueness. You can express this linear combination uniquely, or there's only one way to write them, okay? Right, so how do we prove that? Pretty easily. In math, you want to prove uniqueness. What you do is you say, hey, let's write this vector v in two different ways, okay? Let's write like this, and then let's write like this, okay? So we can always do that because, again, these vectors v1, v2, all the way to vn, they are not any type of vectors. They are the vectors that are in the basis, okay? So this basis vectors span the space, so right? So every vector here can be expressed as a linear combination of v1 all the way to vn. So the same v, these are the same v, okay? They are the same v, all right? So this same v can also be expressed, suppose they have been expressed differently, expressed like this. Then what we want to show is that actually the k1, c1, k2, c2, they're actually the same. And how do you do that? Easy. You take this first equation and subtract the second equation. So take first equation, subtract the second equation. V minus v will give you the zero vectors. And then here, this one and this one here will give you k1 minus v1. Sorry, this will give you k1 v1 minus c1 v1. So you can factor out the v and you can write like this. Okay, so you can write like this. Right, you have a zero vectors, and then you keep doing it, and you will see that you have like kn minus cn vn. All right. Okay, so I am claiming that this part here, okay, this part here, all this here has to be zero. These are all zero. Why is that so? Again, reason is v1, v2, all the way to vn. These are not any type of vector. These are bases. So what does basis? What does basis do? So basis has two properties. Number one, they span. When do we use that? We use it here. Number two, what do? They are linearly independent. What does linearly independence means? Means that if you set this equations, okay, to 0, and you have scalar, this is a scalar, right? These are all scalar, right? Right? These are all scalar, right? So if they are independent, all this scalar here has to be 0 in order to get 0. In fact, that is the only way you can get 0. So your k1 minus c1 has to be 0. Your k1 minus c1 has to be 0. That means your k1 is c1. k2, okay, minus c2 has to be 0, so your k2 has to be c2, so on and so forth. So that's the reason why you get k1 has to be c1, k2 has to be c2, all the ways to kn has to be cn, right? Which means that if you try to express a vector differently, if you try to express the same vectors differently, you can't do it. They are the same. k1 is c1, k2 is c2, kn is cn, so on and so forth, okay? So this proves the theorem that say that if you have a basis vector, you have to have a basis. Otherwise, this is not true, okay? So we have to have a basis vectors. Then if for any vectors, you can express the vectors as a linear combinations of the basis vector here in exactly one way, okay? You can express it uniquely. Okay, so that gives us the concept of coordinates. We can use that to talk about coordinates. So let me tell you how coordinate is defined, okay? So every time you have to talk about coordinates, you have to talk about a basis. So a basis has to be given first, okay? So you have a basis. So you have a basis consists of vector v1, v2, all the way to vn. So this is a basis for a vector space v. So every vectors can be written like this. Now, I am going to collect all these scalars. So these are scalars. These are just numbers. Your v1, v2, all that thing might not be numbers, okay? So think about it. So think about your PV here is polynomial of degree m-2. So all this V here are actually polynomial, okay? These are all polynomial, but the C here, C1, C2, all these are still numbers. They are numbers, okay? So I'm just saying that C1, C2, these are all scalar, these are all numbers. So for any vectors V, I am going to take all this number, put them as the column vectors, and I'm going to call this the coordinate. The coordinates of this elements V, okay, relative to this basis S. All right, so for this basis S, okay, I am going to label this objects V as this Rn vectors. So we're going to use this Rn vectors as the coordinates for this vector V, okay, for this vector V right here. So think about it this way. So think about you go to a grocery store. So your grocery store has a lot of stuff. You have like meat, you have like milk, you have like Diet Coke, you have laundry detergents, you have wine, you have beer, you have all kind of stuff. So the merchandise are different. They are different, but they are all labeled by a barcode, and the barcodes is a set of numbers. So the objects that we're looking at, they are different. They are milk, they are meat, they are wine, but the labeling is numbers. So the labeling here, this is our labeling. This is how we want to label them. So the concept of labeling, okay? So the concept of labeling is the concept of giving it a coordinate. Okay, so the concept of labeling is the concept of giving them a coordinate. Now, we want to make sure, the reason why we need to have a basis is because we want to make sure every object is labeled. So every object is labeled. That is the concept of span. We want to make sure every object is reachable by the vectors in that basis. Okay, so we want to make sure every merchandise is labeled. You don't want to pick a very expensive wine and you go to the counter and they will be like, sorry, we don't have information on this wine, because that merchandise has not been labeled. You don't want that. Another thing you want in terms of labeling is you want it to be unique. You want to have one object labeled to a coordinate, and that coordinates always refer to that object. Think about it. If my social security number and your social security number is the same, this is very, very bad. So labeling has to have two property. Number one, you want to be able to make sure that every object is labeled, and you want to make sure the labeling is unique. That's the reason why we really, really need to have a theorem like this. And we've seen that having a basis really give you this unique labeling, and basis also make sure that you span, so everything will be labeled. So that's how we get the concept of coordinates. Okay, all right, so let me show you how do you actually do that. Let's look at a very easy example right here. So this is a very super easy example, and this is kind of weird. Sometimes the easy example looks a little bit weirder. I'm going to show you why. Okay, so you have a vectors 4, 5. That is in R2. This is our standard basis. Okay, so what is the coordinate for these vectors? Well, relative to this standard basis. So according to our definitions, we have to figure out what are the scalar K1 here and scalar K2 here so that you can get 4, 5. Well, obviously this is 4. This is 5. So by our definitions of coordinates, our coordinates relative to this standard basis is 4, 5. Okay. Why is that vector 4, 5 has coordinate 4, 5? What are you talking about? Well, it's because all the so-called vectors that you know, like the way we write all this thing, they are actually also coordinates relative to the standard basis. Okay, but we can change basis. We can change basis in the homework problem. We'll see why we change basis sometimes. So we can change basis. We can have a different basis now. Same vector 4, 5. There's the same vector 4, 5, but different basis now. The question is, what is the coordinate now? What is the coordinate? Okay, so what is the coordinate for these vectors relative to this basis? What do you think? Okay, so same vector 4, 5. I want you to find the coordinates. Okay, relative to the basis. You have a new basis. These are not the standard basis. What your answer should be. Okay. All right, I will give you a moment to think about these problems, and you should pause the video, and when you have the answers, you should restart the video and we will look at the solution together. Okay. Okay, how do you do that? How do you answer these questions? Again, as I said, you don't have to do anything, just follow the definition. So let's follow the definition. So we want to write 4, 5, okay, as a linear combinations of 2, 1, and 1, negative 1. 2, 1, and 1, negative 1. We want to find K1, K2. This K1, K2 will be the coordinates. the coordinates of these vectors relative to the basis. Why we keep saying relative to a basis? It's not because that we love Einstein so much. It's just because because the coordinate will change if your basis change. Okay, so everything will have to be relative to a particular basis here. So let's follow the definition. Solve for K1 and K2. This is very straightforward. I skip all the details, but you can see that 3 of this 2, 1, and 2 of these vectors give you 4, 5. So by definition, this 3 and this 2 here, okay, is going to give you the coordinate for this vector 4, 5. So if you change your basis, your vector 4, 5 has a new coordinate, which is 3, 2. So in the homework problem, we talk about why we sometimes have to change basis, okay? So we have to change basis, and if you have a different basis, you will have a different coordinate for the same vectors here. And how do you do that? Well, you make sure you just follow the definition and find the K1 and K2. Make sure that this 2 vector here has to be coming from a basis, because if not, you might not have existence, because the things, if you just randomly picks 2 vectors, which are not basis, then all the step could fail, because you might not have solution for the system if they didn't span the space, and if you have redundancy, you have dependency for your vectors, you might not have uniqueness. So we really need to have basis vectors, okay? All right, let's switch gear and look at this polynomial of degree at most 2. Obviously, we already know this is the standard basis. This is another basis for the polynomial of degree at most 2. So let's look at this standard basis. If you are given a polynomial, okay, so now this is a polynomial. So this is a polynomial, okay, and we want to label them, okay? So we want to label this polynomial. And how do we label them? Well, what are the bases are we using? If we are using our standard basis, 1x and x squared. So if you set k1 of 1 plus k2 of x plus k3 of x squared and set it equal to this, you can see that your k1 here has to be 1, right? Your k2 here has to be 2. Your k3 here has to be -1. So 1, 2, -1. Because of this, 1, 2, -1 will be a coordinate for this polynomial. So look very carefully. Our objects that we try to label is a polynomial, but our labeling, like our barcode here, is always numbers. These are always a column vectors, okay? So a columns of numbers. So it's always a column vector. This is actually an element that is in R3, okay? So always remember your coordinates is always an element in Rn. Doesn't really matter what vector space are you in. Your vector space could be a vector space that consists of polynomial, consists of matrices. It doesn't really matter. Your coordinates is an element that is in Rn, okay? Right, so this is pretty straightforward because we are dealing with standard basis. So if you are looking at B2, so B2 is a little bit more complicated now. So B2 here is not our standard basis. So if you are looking for the coordinate, right? So you're looking for the coordinate for this polynomial 1 plus 2x minus x squared relative to this basis B2. So you have to find k1 of 1 plus x, right? Plus k2 of x plus x squared. Right, look at this, okay? K1 of 1 plus x, okay? K2 of x plus x squared, and then K3, okay? K3 of 1 plus x squared, and you want to set it equals to 1 plus 2x minus x squared, so you set it up. It's not so obvious to see what are K1, K2, and K3 now. It's not so obvious, okay? Because we are not dealing with standard basis, so things is a little bit tricky, but we know how to deal with it. So K1 of this, K2 of this, K3 of this, and you want to solve for k1, k2, and k3 so that you have 1 plus 2x minus x squared. This is the same polynomial as the one that we have before. It's the same polynomial as the one that we have before, and you will see that we need 2 of this, 0 of this, and -1 of this. So by the definitions, this same polynomial, the same polynomial from before, the polynomial that we have before, has a different way of labeling it, right? So the coordinate will be different. The coordinate is taken as the coefficient for all this basis vectors. So the coordinate will be 2, 0, -1. So 2, 0, -1 is the coordinates of this polynomial relative to basis B2. So relative to basis B2, okay, you have this coordinate, 2, 0, -1. The same polynomial, what's the coordinate relative to basis B1? Well, that will be 1, 2, -1. But in any case, your labeling is always a component that is in R3 in this case, okay? All right, so that's the concept of coordinates. Not very difficult at all. Once you have a basis, you can always find a coordinate for vectors that is in that vector space. All right, this concludes our discussion on basis and coordinates. And then in the next sections, we are going to look at the concept of dimensions. It is a pretty easy concept and it's very, very closely related to the concept of basis. In fact, I can tell you right now what the dimension is. So dimensions is nothing but the number of vectors in a basis. So the number of vectors in a basis is going to be known as the dimension. But obviously we have some technical stuff that we have to deal with. For example, if you have a basis for a vector space and then you have another basis for a vector space, how do you know that the number of vectors in the first basis and the number of vectors in the second basis is actually the same? Because if they are not the same, then we have a problem, because then the dimensions that we define for that vector space could be two different numbers, and that is things that we don't really want to. So we'll look at all that in the next video, and I will see you there. Okay.